here. Catch up. We'll let the other ones catch up. But it's a great pleasure to have Sebastian Mizera here. He is going to tell us about scattering amplitudes and intersection theory.
Okay, hello everyone. Thank you for coming, and thanks for the invitation to give this seminar. Today I will be talking about this surprising relationship between a topic in pure mathematics that has a surprising relationship to some things that we've been discovering in scattering amplitudes. Okay, so let's start. I'm going to start as a motivation part with just telling you briefly about this mathematical object. So let's start with pure math. And let me consider some complex space. So some complex manifold, which I will call M. Okay, so it's some space. You can think of it as some projective or affine space. And from it, I will remove some singularities from the space. Okay, so you can do something like this. So these are some singularities. And to each of them, I will assign some number. So you can think of it as some number alpha 1, or 2, or 3, say. So you can think of them as some weights, which could be, for example, real numbers or some abstract objects. And to this space, well, you can do a lot of things on this space. You can define some integrals, etc. However, we'll be concerned with a new class of geometric invariants. So that's mostly due to work of Chow and Matsumoto. So they appeared almost simultaneously in works of different authors. The other ones are Delin and Mastow, and also the work of Saito. So these are papers from the 80s and 90s. Instead of algebraic geometry or algebraic topology literature. And what they considered is some two differential forms that we call them phi plus and phi minus. So these are some differential forms on the space M. Later on, it will turn out that there are actually some cohomology classes, but for now, as motivation, let's just think of them as differential forms. And if we have a pair of them, we can compute a bilinear invariant between these geometrical objects. And roughly speaking, in quotation marks, it will be given as an integral over the full space of a wedge product of these two things. Okay? So this object is called an intersection number. Intersection numbers. Of these differential forms or cohomology classes. And the question that we began to start asking around 2 years ago is there a physical interpretation? Is there a physical interpretation of these objects? Of intersection numbers? And the answer is yes, and that's why I'm here. What I will try to convince you of during the course of this talk is that these invariants, where previously they just appeared as some abstract objects in math literature, actually compute certain scattering amplitudes, at least at tree level, of various quantum field theories of the type that we see in nature, such as GR or Yang-Mills amplitudes.
What is this invariant under?
So this, I'm not sure what the exact question was, but it will turn out that if you come up with some differential forms on this space is decorated with these additional numbers, it will turn out that these integrals actually localize. And they become some functions. So the result of this computation will be some function of these invariants of these weights that I associated to.
So these are some topological invariants or what?
Yeah.
Of the manifold.
Yeah, but they depend on these numbers.
And how do you choose this form exactly? They're not arbitrary, are they?
That's what I was describing.
Okay.
Yes. Very good. So the physical interpretation will be when we set our manifold M to be the moduli space of Riemann surfaces, actually at genus 0. So let me plug it in straight away. Riemann spheres with n punctures. Okay, so this is typically called MON. And I'm sure you all know about the space, but to bring everyone on the same page, let me briefly define it and review some of the properties. Okay? So what we mean by MON is that it's a configuration space of n points on a Riemann surface. At genus 0, it's just a sphere, CP1. And in coordinates, and this is quotiented by the action of SLC, by the conformal group. So we'll typically use this action to fix positions of the free punctures, say the first one, the second last, and the last one, to 0, 1, and infinity respectively. Okay? So that means that in coordinates, we can express the space as being the space of the remaining punctures. Each of them lives on its own sphere, CP1, so the whole space is n-3 dimensional, but from this space we have to remove places where punctures collide. Okay? Very good. So how does it look like? Well, the way it looks like is exactly of the type of manifold that I'm just erasing. Okay, so we have our MON, some big space with this dimension, and then through it we remove these hypersurfaces. Okay, so what I mean here is that each point on this moduli space corresponds to a given Riemann surface at genus 0 with some specific combination of positions of the punctures. Okay? Each singularity was the place that we just removed. So each of them corresponds to a certain Zi coinciding with Zj. So that singularity is when two or more punctures collide with each other. So what happens in the neighborhood of each of these singularities is that the configurations on the corresponding Riemann surfaces look like this. That say when Zi collides with Z2, it looks like it lives on its own surface with the remaining punctures on the other side of an infinite front. Okay, so that's kind of a factorization property.
Can you repeat that?
This piece?
What you just said, yes.
Yeah, so when two points coincide, I can conformally map it to this configuration, in which we have one sphere on one side of the throat with punctures, the specific two punctures, and the remaining set on the other side of the throat.
So those are the two punctures that are coincide.
Yeah, these are Zi and Zj.
I mean, what's happening? And then you're taking a limit where those two are going together, or?
Yeah. So as you approach here towards the singularity, you get this kind of factorization. So this is
you're not on the singularity.
You're not on. Yeah.
What about the intersecting singularities? Does that look
Yeah.
the same
So,
with the extra points, or look worse?
yeah. So when you approach these points, you get more and more refined singularities, and in the maximal degeneration, everything decomposes into trivalent graphs, and that's how you see Feynman diagrams arising from the multi-spaces. Okay, so let me now quote some topological properties of the spaces. Okay, so some topological properties. The first of them is quite simple, but it will be important later on, is that this space is non-compact. And this is just the consequence of the fact that we removed some places from our original manifold. So this space has boundaries, and in particular it's non-compact. Okay. The other one is that it's aspherical. And what this means is that only the first homotopy group by 1 of MON is non-trivial. So let me just remind you what this symbol means. Pi 1 classifies all the loops on our space. So you can draw, for example, this loop starting at this point and then going around back to itself. So let's say this singularity was called when ZK and ZL coincide. So let me call this loop gamma of KL. Okay? And what a space being spherical means in this language is that these loops are all we need to know about the space in order to describe it topologically. Okay, so what happens here is that you can think of it as at the beginning of the sphere we have this configuration where this is some K and L. And as you go around, the punctures go around each other. So there's another sphere at the end point here where they went around each other back to the original positions, but they sort of braided like this. Okay, so that's why this group is often called also pure braid group. It describes this kind of braiding properties of punctures on Riemann surfaces. Okay, and the final piece of information that we will need later on is the topological invariant that we can associate to the space. This is called the Euler Characteristic. And in this case, it's equal to, Euler Characteristic is equal to up to a sine 2 n minus 3 factorial. Very good.
There's also called Hilbert scheme of points.
The what?
Hilbert scheme of points.
I'm not sure about that. Okay, so I just told you that the full topology of MON is classified by these loops, like this one. So let me now consider a representation theory of pi 1. Okay, so what this means is that to every element of this, I want to associate some representation, which is typically an element of some GLM. And to make life simpler for the first part of the talk, I will set M to be equal to 1, which is the same as considering abelian representations of this group. Okay? So what that means is that if I consider some loop here, like gamma KL, like this one, what I want to have is a way of associating to this loop some number. Okay? So GL1 is just some complex, non-zero complex number. Okay? And the way I will do it is, well, I already have some loop, so let me just integrate over this. And what I need to integrate here is some one form. So let me just call this DW. So this is a one form. And you can check, in order for this to have a correct representation property, I need to exponentiate the result. So for example, if the loop was just, you could shrink it to a point, the value of this integral would be 0, So exponentiating 0 is 1, which is the identity element in my representation. Okay. But this, of course, leaves me a degree of freedom that I can choose this one form. Okay. So let me just make a particular choice, which will be motivated later on, a posteriori. So let me choose a particular W. So this is some kind of a potential on my moduli space. So let me choose it the following way. Let me sum over all particles ij from 1 to n. Then put here a log of zi minus zj. Okay, so the usual potential on the sphere. And let me put here pi.bj, the corresponding kinematic Mandelstam invariance for this specific collision. And because I need to exponentiate this result later on, and this is some mass dimension, I need to put some mass scale here. And this mass scale, I can as well just call it alpha prime, like the one that appears in the string theory. Okay? Just some number. And you can show that just the requirement, just putting this potential and requiring that that forms a representation of this group implies that the spectrum of my particle, of my masses, is quantized, meaning that pi has always has to be a half integer multiple of my alpha prime, 1 over alpha prime. And for this talk, so it means that the only states that are allowed are these towers of multiples of 1 over alpha prime. But for the purposes of this talk, let me consider only massless scattering. So all external particles will be massless. Any questions?
You mentioned the word scattering. Should I think of the punctured sphere to be the one in which every puncture is represents an incoming
incoming vertex operator.
vertex operator?
Yeah.
Okay.
Can you say again what pi is?
So I didn't say that. So to every puncture would associate some momentum. Let me call that here there's some momentum to cave puncture that will be pk associated to this. So what I put in my potential is just the Lorentz contractions of this momentum.
Oh, sorry, that's a dot product between.
Yeah.
Oh, I'm sorry. Okay.
And now we'll additionally require that all the momenta squared to 0, i.e. they're massless external states.
How unique is this W?
It's not unique at all. That's my choice. So that's what I choose.
But something must not change by the choice. That is
Actually, so every
integral. Yeah, go on. Yes.
every choice would correspond to a different representation. And I choose I make this specific choice for something that I will motivate in 10 minutes.
Okay.
Okay, so now this
Can I
is
just ask several more questions? You said the inconsistency of this is what gives you the quantization condition.
yeah. Should I derive it?
No, that's okay.
It's very simple actually. So what all it says is that I have my sphere, I have my point somewhere here.
Okay.
There's also this point at infinity that naively this d of this it has poles at infinity, but infinity is not a special not a special place. So requiring that I have this loop that goes around infinity, shrinks to 0, it should be an identity element of my representation.
Oh, then you said
And
you just
requiring
get
that
this
gives you some condition on p,
Okay.
and that condition turns out to be precisely this.
Okay.
So now I will introduce a covariant derivative. after all, we already have our one form. So how about, just like in gauge theory, how about I couple it to the usual derivative? I call the result some covariant version. So it's the usual differential on some space, twisted by this dw. Okay, so that's something that actually comes out of naturally out of this formalism, but I wanted to make a shortcut. Okay. Once we have this, we can define something called a twisted cohomology. Okay. So what this means is that I consider the kernel of my covariant derivative quotiented by the image, or the exact forms modulo the closed forms, but with respect to this new connection. Okay. So that let me just call, so in the math literature this would be called H of K of MON with this connection. But for the purposes of this talk, let me just call this HK of dW. That K, where pure K means that we consider K forms. Okay? So this space is the space of K forms, which are closed but not exact, exact but not closed with respect to this connection. And here we can quote a famous result of Aomoto, who showed that only the case when K is the maximal dimension, only in this case, that space is non-trivial. Okay. So what this means is that if I consider the space of forms transforming with this connection, the only ones that are allowed are the ones where the form has degree n-3, which was the same as the dimension, the complex dimension of this space to begin with. If you try to write down any other form with this property, it will turn out that it's always in the image, so it's always trivial.
Is that true for any W? Or any
Yeah, that's true for generic and up W. Yeah, very good. Which in our case translates physically to the fact that the kinematics is non-resonant. So kinematics is non-resonant. So what this means is that any subset of points I, subset of particles, is non-zero. Okay? If that was true, it would be sitting on a factorization channel. So what I'm saying is that as long as we don't sit on any particular factorization channel, we're just in generic point in the kinematic space, this is always true.
H0 also.
It's also true.
Trivial. 0?
Yeah.
They mean just the complex number.
Yeah. Very good. So that might seem like a sort of an abstract result, and it is an abstract result. But what it buys us is the connection between what I mentioned before, which was the Euler characteristic. So Euler characteristic chi can be always written, or in those cases, it can be written as an alternating sum of the dimensions of these cohomology groups. Okay, K goes from 0 to infinity. But I just told you that the only non-trivial cohomology group is the one where K is equal to n-3. So that tells me that all the terms in the sum are 0 except for one, the one that we care about. And it's equal to minus some minus sign, times the dimension of this group with n minus 3. And from the result that I told you before is that this Euler characteristic is always a constant equal to n minus 3 factorial times the same sign. And from this we can conclude that the number of different forms of the dimension of this space is n minus 3 factorial.
Is there a relation between these differential forms and the vertex operators we encounter in
Yeah, that's the next slide.
Oh, okay.
But for now we have this number appearing, and if you're familiar with scattering amplitudes literature, this number reappears later on over and over. Okay. So let's get back to some more physics. So what does it mean? It means that we want to convert these sort of abstract objects, these cohomology classes. We want to convert them into numbers. Okay? So really, what we want to consider is some families of bilinears, which tell me that pairing two of such objects can become some number or some function, and that function should have some physical interpretation. Okay, so let me first of all pair up this cohomology group that we talked about all along, together with its antiholomorphic counterpart. Okay, so here we'll have some differential form of this degree, and here we have some differential form which is antiholomorphic of the same degree. Okay, and it turns out that if you ask for this, what comes out is this kind of integral. Okay, so if there's some differential form phi, and some phi bar, then the answer is this.
So I thought you were doing complex Durant cohomology with values in this line part.
Yeah.
Now we're doing Dolo.
Yeah. Or you can do everything real. Just intersect this with n minus 3 0 and 0 n minus 3 for this part.
But there's some Hodge structure on the cohomology that
Yeah.
you mentioned.
Yeah. Okay, so we have our holomorphic and the holomorphic part, and there's this piece that if you plug in the W that we had before, is just equal to Zi minus Zj by power of alpha prime Pi dot Pj. So from this you recognize that this part is nothing but the so-called Covariance factor in string theory. And it tells me if these cohomology classes are chosen appropriately, such that they can come from some vertex operators and so on, then these objects contain me closed string scattering amplitudes at tree level. Okay, so it's something that has left movers and the right movers and this Covariance factor. Okay. Similarly, so that gives you some intuition about what this space is. It's really the space in this physical interpretation, the space of sort of left-moving and right-moving correlation functions prior to integration. Similarly, we can consider a pairing of this cohomology class with its corresponding homology. So this means it's a homology. I don't really want to discuss it too much in this talk, but you can trust me that what comes out of this is an integral of this type. While we have a single holomorphic form integrated over some integration cycle. And once again, if you appropriately identify this with some left-moving correlation function, this is the type of object that computes open string scattering amplitudes, G0 scale. And as a matter of fact, this understanding of amplitudes in string theory as pairings of various vector spaces allows us to link these two types of objects by so-called KOT relations. And that's something that Eduardo Casali was talking about a couple of months ago here in this seminar. So I don't want to repeat any of that.
So the way I should think about this is the setup that you're wasting right now, I should do was all actually holomorphic. And then I should just take the anti-holomorphic copy of it
Yeah.
on the right-hand side in the top line.
Yeah.
And the left-hand side, there's a homology rule, cohomology and pairing.
Yeah. And the homology has the same property because it's
Well, it's not totally clear, it's not compact, but I guess I'll.
yeah, I sort of glossed over that. Okay, so what this tells us is that, but I will come back to the compactness in a second. What this tells us is that these are some abstract objects that come out of this algebraic topology literature. And so far, the two of these objects have some physical interpretation in terms of scattering of strings. And if you follow this literature of people studying these invariants, there's one additional invariant, which looks as follows. If you consider the cohomology group that we talked about, and then you pair it up with its dual, but instead of considering anti-holomorphic pieces, I will just add a minus sign here. Okay? So let's call an element of this object phi plus, and of this space phi minus. And it turns out there's a object that you can associate to these two forms. So once again, it's going to be an integral over the moduli space with phi minus wedge phi plus. And that's the intersection number that I was talking about before. So really, these two differential forms are elements of two homology classes. And now the question is, what is the physical interpretation of this?
Sorry, before it was important that you had either the W measure.
Yeah.
So now is that being absorbed into the definition
Well,
of
you
phi
can-
plus and minus?
You can think of it as having e to the w, and we still have e to the minus w.
Yeah. Oh.
Previously it was a bar, now it's a minus, so they cancel out.
Oh, the answer is so there's actually just a minus sign. This is not some notation for dw bar.
No, sorry, this is the same cohomology group,
Yeah.
but putting a minus sign up front. Yes.
So this is a Tapian amplitude?
Yeah,
What you calculate, because normally I also would have vertex operators, right? I mean, normally I do a correlation function and then I integrate it over the moduli space. And so the integral you have written down is over the moduli space.
Yeah.
So, but where are really my correlation functions?
It's all in here. So you're right that if we choose this to be just some top differential form like this, and that to be the anthropomorphic part, that all we have to do is integrate this combination factor with nothing here, and that would be tachyon amplitude.
Yeah.
But that's a specific choice of what this cohomology class means. There could have been some more complicated function here, which could depend on z, could depend on p, on some polarization vectors and so
Yeah,
on.
so when you would have a polarization, like for example for a graviton,
Yeah.
so then you would have, so then the value of your differential form changes, so
Yes.
it becomes valued in the U1, for example, when I'm on a torus or something like this.
Yeah, it will depend on some Mandelstam invariants. So in principle, it could be some f that depends on the positions of the points
Yeah.
on p dot p invariants, on p dot epsilon, and epsilon dot epsilon. And I will show you an explicit example of this form later on.
these families are parameterized by the space of n minus 3 forms on M0.
Yeah. Okay, so we know roughly speaking, if you perform these integrals, you get some gamma functions in the simplest example, similar here. So now we can ask the same question here. What type of results do we get from integrating these intersection numbers? And a surprising thing is that even though we perform the integral over the full moduli space, the result always turns out to be a rational function. Of kinematic invariants, so Pi and Pj, and possibly of other invariants that can appear in these differential forms. So let me just call it epsilon, epsilon, maybe some colors, and so on. But the key point is that the fact that it's always a rational function. And the second property is that you can show that this object always has a finite number of simple poles of the type one over sum over kinematic invariants, possibly shifted by some integers. Okay, and here again the key statement is that it's a finite number. So in contrast with these more general objects, these ones look like QFT amplitudes because they're rational functions, like the ones that come from finite diagrams, and they only have poles in these places. So that means this suggests that these intersection numbers physically should correspond to some new formulation of QFT scattering amplitudes. And right now we understand that this is the case, and we have a lot of explicit examples. But
where does this reside, this QFT? Where does it live?
Meaning,
It's not a wall sheet, obviously. It's not target space.
yeah, so
the space in which this field theory lives.
Yeah, that's still an open question.
Open
so
question.
We have this new way of computing QFT amplitudes. It looks like string theory. It must be some type of
Topological.
But you know it's modeled on this kinematics with P, right? Then you have P. This is external data. You've attached a complex dimension and space or whatever to punctured.
So
the
it's
same type, right? So you at least know the dimension of the target.
We're at tree level, so the dimension of the target doesn't even matter.
It doesn't?
It doesn't. At tree level, even in string
No, I
theory.
mean when you tell me what P1 is, you have to tell me the dimension.
Right. No, but what I mean is that we only supply these dot products. So these dot products don't care about what the P mu. I mean, if I just supply this scalar invariants, they don't care about what's space-time
It
dimension.
wasn't scalar invariance. It was data attached to every puncture on your sphere.
Yeah.
So you copy. There's a space in which the data takes values. That space has to be the same for every puncture on the sphere.
True.
So that's a copy of your target space.
Yeah. So you can take it to be some d-dimensional.
But there must be some anomalies, surely.
No, at tree level they wouldn't appear.
Sorry?
At tree level they wouldn't appear.
They wouldn't appear.
Yeah.
But in some sense they would appear, right? Because what you are using is a certain ghost structure by doing the integral over the moduli space. I mean, this is also what you do in closed string field theory. And so for this ghost structure to work, you want to have a vanishing anomaly, conformal anomaly. So that's why I think so the anomalies should be also relevant there.
It's a world sheet anomaly you're talking about.
Yeah.
Yeah.
Talking
So.
about target spaces.
No, I mean, I'm talking about the worldsheet anomaly, which is connected to the target space dimension.
So maybe let me just summarize this discussion by saying that what I'm proposing here is some model that lives on the moduli space of the MON. It's still an open question, what is the corresponding worldsheet model that corresponds to, that gives rise to these integrations?
But normally when you do this in string field theory, so what you have is, so this correlation function comes from your CFT data. So, but you can put any CFT you want. So what you are interested are really in the properties of the Riemann surfaces and in the integral over the moduli space. So you decouple it in some way. So, and this is exactly what closed string field theory, for example, is doing. It says you can take any CFT as long as you do not have a conformal anomaly, and I do not really care which one you take, whatever you want, but I really only care about the integration over the moduli space and how exactly what you are doing. So you have your pair of pens, and you want to glue them together, and this is exactly the degenerating Riemann surfaces which you get in your diagrams. I mean, it looks very, very similar to.
Yeah, it does, and I agree. And perhaps we should discuss it more later on.
But there you get the target space. So the target space interpretation then comes from the CFT, and that you have an anomaly-free CFT.
Yeah.
So gives you constraints on the dimension of the target space.
Yeah.
Can I have a quick fantasy here? Just quick one. Could that possibly probe a topological sector of the string theory that you know and love? Meaning that some sector where you really have a topological sector where what would be normally a gravity theory. And we know that whenever you have a such sector, a topological sector, there's some room for dynamics on the boundary, which you can think of as CFT. So this could be a boundary CFT. I'm just fantasizing. But you're open. You're not non-committal.
Yes.
All right.
There's a proposal for having that. No, there is.
Right. Could possibly be.
So, I mean, he's not telling you all this stuff, but of course there are these twisters that top out like this, and then there's even limits of ordinary string theories that are singular that get you to the twister. So there's a whole picture that you could probably paint.
Yeah, let me just emphasize the twister formulation is something that I will go back to later on. Let me just emphasize that at some point I claimed that this works for any mass dimension, any mass of external states that lies in the spectrum. So that's in contrast with string theory, which always, ambitwister string theory, which always assumes massless external
Is there
states.
two missing there, or is it not important?
No, this is correct. Yeah.
So that's interesting.
It might possibly be.
It's shifting it away from all the physical poles.
Yeah, it only takes half of those. I never managed to understand why, but yeah.
Is the reason you have QFT rather than CFT in your statement, is it because you have some mass scale around or what?
So sorry, QFT is the target space, QFT.
Yes.
And CFT, you mean the worldsheet CFT?
No, the effective, the QFT you're talking about here is QFT, not some new CFT.
No, it's QFT and of the types that we know
And it is
about.
really QFT, so that there's some mass scale somehow.
Yeah, there is this mass scale, and the mass scale is
alpha
what
prime.
I called alpha prime.
Okay.
Although I could have called it mu or something like this. Okay, very good. So let's postpone more discussion towards the end. What I wanted to highlight.
So just, I didn't have this question in my head, but, so this alpha prime can be the effective dynamically generated mass scale?
It could be, yes. But as I said, there's no worldsheet model.
No, but it's interesting that that's appearing already.
Yeah.
In the twist.
So very good. So let me call from now this object is some invariant of phi minus and phi plus. Let me use this bracket notation to denote this object. And in order not to forget that it really depends on this twist, let me add it here. Okay. So one key point is that this integral, actually, which relates to William's question before, is that this integral, as written here, doesn't really make sense. So I treat it a little bit. And this is related to the fact that MON is a non-compact space. Another issue is that naively, if I take two top holomorphic forms on some space and I wedge them together, they would give me 0. Okay? there's a sort of an anomaly, you can say, close to the boundaries of the moduli space, which is that close to the boundaries we could have some divergences. Okay? So on one hand we can have divergences, on the other hand there's a zero here. So we really have some kind of a 0 over 0 type of problem. So we need to regularize this problem. Okay? So the way to regularize it is to add, to really compute it with a form phi plus c, which says that phi plus c has compact support. And what this means is that we're supposed to find some differential form which is in the same cohomology class as the original one. However, it should have the property that it vanishes close to all the boundaries of M. Okay? So compact support means that phi plus c has to vanish near all boundaries. And that's actually one of the signs why this object here is going to localize, because once we impose this compact support, what's going to happen is that this is still true at phi minus phi plus is equal to 0 in the bulk of M1. However, what we've just regularized is this problem close to the boundaries. Okay? So what this tells me is that this integral doesn't receive any contributions from the bulk of the moduli space. It will localize on the boundaries. And we already said at the beginning that boundaries are exactly the places where things look like Feynman diagrams, and that's in fact related to these two issues. Okay? And that's the reason why this can become a QFT amplitude, not a string theory one. So in the last,
so we still have rational functions and nice, like all these nice properties that do not damage the function class.
Yeah, let's do an example. So example will be at 4 point, 2-to-2 scattering state, in which MO4 is parameterized by 4 punctures. Okay, so we fixed 3 of those to 0, 1, infinity, and the remaining one, Z2, let me just call it Z. Okay, and in addition, this covariant derivative now is d, or d plus alpha prime s over z, in this gauge fixing, d over z minus 1, which is z wedge. Okay? And now what I want to do is impose this compact support. So let me draw my space and move forward. How it looks like, it has some boundaries close to 0, 1, infinity. And this is the Z space. Okay? So these are the boundaries. So what I want to do is remove some, look at some small neighborhoods of these boundaries, and impose that there exists some phi plus C, which differs from phi plus only by these total derivative terms. Okay? Such that the result is 0 exactly everywhere inside of these circles. Okay? That's what it means to impose compact support. Okay? So let me just give you an answer. The answer is that what you should put here is that we're going to sum over all boundaries, points, 0, 1, infinity. And what I'm going to put here is a step function, which is, the step function, which is going to impose that the sum has only support inside of each circle. Okay? So this piece is 1 inside of each circle and 0 outside. And here I will add this formal inverse of my covariant derivative. Okay? That's the proposal. So let's see that it satisfies what I want. Okay, so what I can do is just take this expression and first act with the derivative on this term. So delta and delta inverse cancel out. And what I get is 5 plus 1, which is just this term from here. And then we have minus a sum over all points p times the step functions. Okay? And the second term is when this derivative hits the step function. Okay? So what that's going to give me is minus sum over all points. Now, if you act on a step function with a derivative, what you get is a delta function localized on the step. Okay? So that's just a delta function, which looks like this, times the remaining inverse. Okay? So the result has the correct properties, namely this is already regularized. So this sum is equal to exactly 0 inside of each circle and 1 outside. Okay? So this is compact support. And likewise, this is already localized on these small circles. So it has compact support as well. So compact support is achieved. Okay? So what do we do with this text? Next, we plug into the original definition, which was that we just take these two forms, integrate them over the whole space, and let me add some normalization factors, some 2 pi I. And here, what we wanted to integrate is this phi plus wedge, phi minus wedge, phi plus c. Okay? So now we have some one form, holomorphic one form, wedged with these two pieces. So the first term is going to be 0 because of the older argument. I wedged a dizzy form with a dizzy form, so it's 0, and only this term survives. Okay? So what I get is this minus sign cancels, and I get plus 2 pi I times some integrals, which now localize on these small circles. Okay? The small circles were around these points. Okay? So there's a sum, p from 0, 1, infinity, and then my full integral now becomes a residue integral around each point. So z minus p really small. And what I get is some phi minus from here times the rest, which is this guy. Okay, so this is just a residue computation.
How do you compute the inverse phi? Do you have a formula for that?
Yeah, so what inverse phi does is that what we really want to do is we want to evaluate what this is. So let me call this psi, the result of this. We just hit it with the derivative the second time. Just to invert this. And you want to solve this for psi. So it's just some differential equation that you need to solve near each p out of 0, 1, infinity. And once you solve this differential equation, you only need to know it in the small neighborhood of each singularity because it enters the residue. Okay? So for example, if I choose my phi of plus and minus to be the so-called Taylor forms, so there's some measure of the moduli space divided by z1 minus z2, 2 minus z2, z3 minus 4, 1. Okay. If we take this form, this is like the covariant version, but now we can apply our gauge fixing from here. Okay. If we do this, then that form is just equal to dz, z1 minus z. Okay, now our only variable. So it has singularities at the origin and at 1. Okay. Now, if we solve this differential equation, you can show that, I mean, it's not difficult to see that if we actually solve this with this choice of, say, phi plus, it's going to be equal to 1 over s plus the dot near P0. So close to this, we get the S channel. Close to U channel, close to T channel, we get 1 over T, and otherwise 0. Okay? And then if we plug this all back into this formula here, this specific example, what we had is that, so let's write this absurdly, 1 over 2 pi I as a residue here. Okay, so what we get is residue around the given point of this thing. We just computed what this per is 1 over s or 1 over t. And then in addition, we need to care about the residue here. And if you do this, the result is 1 over s plus 1 over t. So there's no really trouble. And that's in fact the simplest example of a scattering amplitude. This is a scattering amplitude in a cubic theory.
That's quite an elaborate way of arriving at a very simple, well-known result. So is the lesson here that you've succeeded in having some profound mathematical framework for this, which will pay off for more difficult problems? What's the philosophy in a nutshell?
It already pays it. So what this tells you is that there's some new representation of these kind of amplitudes. Of course, here I showed you the simplest ones. But the ones that we really care about are the scattering amplitudes in Yang-Mills or gravity free. So of course, if you try to do those things with Feynman diagrams, you will run into problems quite quickly. So what this formula gives you is an alternative way of computing the same object. On top of that, in a way that sort of doesn't use Feynman diagrams in the official formulation.
Well, this is tree level, right? So
Yes.
what can you remind us the difficulty?
So if you try to compute 5-point amplitudes in GR.
In GR, yes. But we are talking string theory correlation functions here.
Yeah. So what I'm saying
So
is
you're
that
saying even at tree level, computing correlation function of 5 strings is
5 gravitons.
graviton, sorry.
The usual
Is a tough problem.
It is a, you wouldn't give it to a grad student, yes.
It's not even around,
It is around nowadays.
but it's a tough problem.
Yeah.
I once did a 3 graviton string scattering calculation, and already this is horrible
It is.
because you have to be very careful also with the polarizations and all the stuff. So I mean, and 5 is probably
And you're assuring us here it will be easier because of this mathematical framework?
I'm saying it's a different representation. I'm not saying it's going to be easier.
Different doesn't mean easier.
No, but it might, I mean, not necessarily. But it also manifests different aspects of scattering amplitudes, which are not at all obvious from the Lagrangian point of view. So perhaps I can finish with giving these 2 different types of localization formulae that we now know about these objects.
May I ask another question?
Yes.
So this epsilon, so is this a cutoff scale? Can you understand it as a cutoff scale when you do a
Yes.
Wilsonian effective action?
No, it's not this.
But this happens in closed string field theory.
Yeah,
This is
that
exactly
you can.
in closed string field theory. You can understand when you go very, very close to this punctured,
Yeah.
then the connections become very, very long. So the string diagrams really look like Feynman diagrams. But normally you can just do this when you integrate out all the higher excitations, because the higher the excitations are, which run, so the more you move away from these punctures. So normally in closed string field theory, and there's a nice paper about this. So this epsilon, I think, can exactly be understood as a cutoff.
Yeah.
So, and everything above this cutoff is integrated out.
Yeah.
And then you get an effective description, and the effective description is exactly given by this getter.
Yeah. So I guess you're referring to a short sentence.
Exactly. So this is what, for example, Sen has done.
Yeah. So if you apply this formulation in this kind of integrals, then I agree you would have this kind of interpretation that you're mentioning. What's happening here is that our integral is this kind of localization integral in the first place, and it really doesn't matter how large epsilon is, unless epsilon is order 1 such that these things start colliding. So it's really invariant of this epsilon scale.
But normally the results are not invariant of the scale.
In string theory they're not.
Yeah.
Here they are.
Also, you're saying because there you were saying you wanted to calculate closed string amplitude. So now you go away from string theory.
Yes, we're computing this new class of invariants, which are supposed to compute me QFT amplitudes, not without
He never
any
said string
tower
theory, by the
states.
way.
Yeah,
We're
there's
putting words in
closed
his mouth. He didn't say string theory, he wrote that down.
there's closed string amplitudes on the
Yeah,
bottom.
that's closed string theory amplitude.
Yeah, but you're not
Open
using
string
that.
theory amplitude. Yeah, this is supposed to be QFT.
Apple, orange, orange, apple.
Okay, yeah, that's good to know.
So now, as the very last step, and I can quote two limits that we can consider. So this was sort of exact computations when we compute the full object straight away, and if you reinstated the alpha prime orders, they're here. But in principle, especially if you compute massive amplitudes, this could be more complicated functions. So it's actually interesting to consider two different limits for computing them, which might give us different insights of how this looks like. So one of the limits is when alpha prime goes to infinity. So this is like masses limit, when all masses go to the origin of the spectrum. And what you can show is that in this limit, this integral localizes on these constraints, which people nowadays call scattering equations. With phi plus and minus going outside. Okay? So there's some sum over points in the moduli space. And this comes with a correction of order 1 over alpha prime. Similarly, you can consider the separate limit. Okay, so separate limit would be alpha prime the exact opposite when alpha prime goes to 0. Okay, that's like the low energy limit, especially in string theory. So here, it can be written as a sum over all trivalent degenerations of my moduli space MON. So these are the limits where the Riemann surface goes into, becomes sort of like a sum over many trivalent degenerations, like this. Okay? So that may be corresponding places where this happens V of gamma, because they're in one-to-one map with some trivalent graphs gamma. Okay? And what you can show is that in this limit, the answer becomes residue around this degeneration of one form, residue of the other form, divided by the corresponding propagators. So these are all edges in my graph, and these are all propagators in the master space. And that formula is valid at the leading order, and there are some sub-leading corrections that look like this. And then what you can ask is, so you see, this is sort of a picture that looks like Feynman diagrams. This is a picture which doesn't resemble Feynman diagrams at all. You can ask, is there some special cases in which these two corrections cancel, such that the intersection number that we started with is independent of alpha prime, and then these two representations are really two facets of the same object. And that happens if we consider, so these cancel, if we actually consider either cubic theory, Yang-Mills theory, or GR. And we've actually seen a manifestation of this here. Okay?
You call GR 50?
Yeah. I'm sorry.
That's unusual.
Okay, so this is a representation that we discovered in discovering amplitudes a few years ago, and there was always this question of how it connects to the usual Feynman diagram picture. What this tells you is that in these special cases, when we don't have any alpha prime corrections, these two objects are really equal to each other, although they don't have to be equal in more complicated cases. Okay, so with that, there's a question.
Sorry, is there a connection to T-duality? Because T-duality, in a way, can be interpreted as a strong-weak duality in alpha prime.
Yeah, so as far as I know, Warren Siegel is working on such questions, but I don't know what's the resolution of this.
And so you say this result also would hold for closed strings?
No,
For normal
no.
closed string? No, this is really something decoupled, so it's a,
Yeah.
it's a decoupled sector.
Yeah, that's actually why people used to be confused about this limit.
Exactly, so this
Because
is strange.
in this limit, you have a localization on the similar number of points, but the localization is really much more difficult if you actually try to do it either here or here, okay? And that's because we really, okay, there's a longer story, but what happens is that localization here really happens on the covering space of MON, which tells you that there's really critical points on each sheet of this covering space, and then there's really infinite number of critical points. They just lie on top of each other, and they tend to resum to resemble these kind of formulas. I can explain.
Maybe we should thank I'm sure there are many more questions, so you guys can have at it.